Bromate 5 ions and bromide ions react in acidic conditions. A series of experiments were carried out and we've had a rate equation determined. It's first order, second order. Our first thing it says is to use the data from experiment 1 to calculate a value for the rate constant K. So the first thing we need to do is rearrange the rate equation to say K equals. So we bring the concentration terms down underneath rate. And then we sub in some numbers. So 2.4 times 10 to the minus 2 divided by 0.1 times 0.2 times 0.3 squared. H plus squared. We type that in our calculator and it does say to give it to the appropriate significant figures, and the table's given to 2 significant figures. So my calculator says 13.333 recurring, but to 2 significant figures that would be 13. Now if we have a look at this, it wants the units. So remembering that rate is the units of concentration and then seconds to the minus 1. And we've got 4 concentration terms on the bottom. So one of our concentration terms is going to cancel, and we're going to have concentration to the minus 3, then seconds to the minus 1. So that's what we get. Now we have to complete table 2, and we've been given space for working. Excuse me. Now row 3 is probably the easiest because we can just put the numbers into our rate equation. So we can put the value that's on our calculator of 13.33, or just even the 13, and we can times by 0.2 and 0.4 and 0.5 squared. So row 3 is probably the easiest, and we get 0.27. You may get 0.26 if you use a more rounded value. It just depends if you use the 13 or you keep the 13.33333 from your calculator screen. Row 2 is not too bad because we can see that this and this bromate and acid have stayed the same, so they don't have an effect. Rate has gone up by 1.5, and because bromate is first order, then this should go up by 1.5 as well, so 0.15. Now the final row is a bit tricky because it's the acid, and so I would suggest that you're probably better off rearranging the rate equation to say H plus equals, and H plus equals the square root of rate divided by K times bromate times bromide. And so if you bang in the numbers from row 4 for that, so you do a square root sign and a fraction sign, and on the top line put the rate, 2.7 times 10 to the minus 2, and on the bottom line put your 13 and your 0.1s, and then press go. And your calculator is going to give you either 0.45 or 0.46, depending on whether you've used a rounded value for K or not. Next part of the question asks us to do an Arrhenius. First thing we have to do is fill in the table. So if we do 1 over 302 on our calculator, we get 3.31 times 10 to the minus 3. And if we do ln of 3.7 times 10 to the minus 2, we get minus 3.297 or minus 3.30. So what we want to do now is plot those points. They've given us some grid, and remember that AQA always give you this grid that's just about the right size. So if we look at our table, our ln 1 over t values go from minus 2.8 to almost minus 4. So if we spread this out on our graph, we can see how we can just nicely fit the whole thing in. They've given us just the right space to really spread it out so that we can really plot those points. So now I'm going to have to do a little bit of scrolling backwards and forwards. I'm going to start at the bottom of the table because that's usually the smallest y value. So minus 2.08, 3.21. Now if we look at this scale, it goes up 20 squares to go up 1. So every little square is 0.05. So minus 2.08 is nearly at minus 2.1. And we are going 2 little squares across, so it's going about here. The next value is at minus 2.71, 3.31. So I'm going to put that, 2.71, 3.31, that's about there. Then we're going to go minus 3.3, 3.39. So 2 back, 3.3. I've forgotten the number. Minus 3.3 and 3.39. 3 and 3.39. About there. And then our last one, minus 3.99 and 3.5. 3.99 and 3.5. So right bang on the bottom there, pretty much, just shy of the very bottom. Now we need to get out our ruler. We need to draw a line of best fit. Trying our best, bit either side. And the next bit it asks us to do is to use it to calculate the activation energy. If we notice here that the gradient part, this is a y equals mx plus c, that our gradient is equal to minus EA over R. So we need to find that gradient. So we need to do a change in y over a change in x. So we need to pick some points. Okay, so we want to find some points to use where we feel happy reading the graph. So it almost goes nicely through the top up there, so we could go there. I think I'm going to take my ruler, I'm going to go here, I'm going to put, use a different colour pen so I can just see it, something like that, and maybe go to here. So this point here is 3.275 times 10 to the minus 3 and minus 2.5. And this point is minus 3.8. And it is it's like a half a square away from 3.4255. So half a square away from, so 3.47 times 10 to the minus 3. So minus 2.5 minus 3.8. 3.275 times 10 to the minus 3 minus 3.47 times 10 to the minus 3. Now there'll be a range of allowable answers here, so hopefully we're inside that. 1.3 over. So I'm getting minus 6, 6, 6, 7. Now the range that the exam board allowed on this one was anything from minus 6,500 to minus 6,800. Now that is my answer, and if we look at the units, that's in Kelvin. Now the gradient is equal to minus EA over R. So minus EA over R equals 6667 Kelvin. Okay, so what we need to think then is to get the activation energy, we need to times minus 6667 by minus R, which they gave us as 8.31. So that's coming out as 55400, but this will be in joules per mole because this is in joules per Kelvin per mole, and we've times by Kelvin, so we're doing joules per mole, and we want it in kilojoules. So we're going to divide by 1,000, and I'm getting 55.4. So the range was between 54 and 56.5.